Alright, so welcome to physics. I am Mr. Potolo, and I will be physics teacher for you. Now, we first want to learn what is physics. Since this is introduction to physics class, I want to start by defining what in the world we're doing. So, a working definition of physics we can work with to define it will be the proximate study of the laws of nature. So, we're taking a look at nature. How does the world, we're trying to answer certain questions. How does the universe work? Why do things move the way they move? Or something like that. And we go into lots of details. There's different subjects through which we'll study. And I don't want to overwhelm you with everything we have to study because this is 1 year course and we only have so much time we cover in during a semester period. So in physics, we're looking at a situation locally. So I'm gonna make sure you write these notes down. So we're looking at a situation at phenomena. So different phenomena that we're looking at, whether it's the motion of a car, or whether it's a swing set, or electric field, or something like moving charges or a circuit. We're looking at different phenomena and we're looking at it from the local situation, what's going on. We're looking at things from a natural perspective, but it certainly doesn't mean the supernatural cannot come into play at all. And we'll talk about different situations where this comes into play. And physics was known as natural philosophy for quite a long time. So you'll see lots of philosophical language being spoken about and spoken of in physics, and I think it's very important to look at the philosophy to understand the physics and why we describe things the way we describe them. And we'll get into more detail about that as we go on. So let's start by looking at chapter 1 in our textbooks. So our chapter 1 is representing notion. And I'm going to cover in this lecture sections 1.1, 1.2, and 1.2. And I will cover 1.3, 1.4, and 1.5, 1.6 another time. Because each point requires some details. So we're going to cover 1.1, which is motion at first look. And 1.2, position in time, putting numbers on nature. And so our primary objectives in this section would be to define motion, I want to define motion. Second thing I want to do is to learn about motion diagrams. Third thing I want to do is to define position. Let's see, define position. Define position, combine it into one objective. Displacement in time. And of course, last thing I want to do that will be it for now. We'll stop there. Okay. Now, objective 1 is of course to define motion. Now, interestingly, motion we'll talk more in detail about in chapter 2. But for now, I want to give us a working definition of motion. So we'll expand this point later. But to define motion, we can define it as movement of something. Or really anything. Oh, my handwriting is horrible. We'll just define it as movement of anything. Now, you notice I don't mention time. This is a characteristic of motion, but it's not what defines it. And we'll explain why that is later. The idea of motion is anything that moves from one place to another. So I'm going to draw a picture for you. Okay. I have a box like this. Let's say it's traveling along the ground, and it goes from point A to point B, which is here. Call that A, call that B. This is motion. It's a movement of something going from some place. We have motion in every single thing. whether it's movement of your pen when you're writing down all of these notes, whether it's my voice molecules or voices, this involves motion. Uh, the nerves in our bodies, even the lights in the room, all involve a concept called motion, which is simply movement. Okay? Now, motion has a certain characteristic to it, that it occurs in time. And to explain that all movement occurs in time. So this isn't a defining characteristic, but I'll explain the caveat to that. So motion occurs in time. Okay? And we'll talk about more in detail this point in a bit. But the idea of what is moving, I have to know when this is happening. It doesn't necessarily have to be specified, but I know that motion must occur within this concept called time, which we will define in a little while. Now, I can draw the movement of something on a motion diagram. A motion diagram is a visual of the motion. So the visual of motion, in short. So it's something that you can see, the picture of some type. You see the example in my diagram that's above in the red. This is a type of motion diagram. I'm showing the movement from one place to another. Now, oftentimes they will tell you to draw this out. Okay? Draw out what is moving, whether it's a car, person, whatever. But it's not always necessary for that to happen. So vehicles are things in which motion takes place, but they are not the defining characteristic of motion. Your book does not make that point very clear. On page 3 in the textbook, it talks about bicycles, baseballs, cars, airplanes, rockets, objects that move. This is true. Okay. But make very clear that the motion is the path on which it's going. Okay? So the motion is not the object itself, but rather where it is going. Okay? Oftentimes you'll hear this term trajectory. Trajectory is the path of travel. I can write that for you right here. Okay. Trajectory is simply the path of travel of whatever object that's being considered. Okay. Now, you'll hear me use the term object and body interchangeably, but we'll talk about the differences between them later. Since your teachers are probably used to defining object, where they talk about an object or something, we'll stick with that terminology for the time being until later. Now, it is important for us to understand that anything that exists, whether it be a book, car, a plane, anything that's rigid, that has a solidity to it, can be formed to make a point. And this happens because the molecules squeeze at what we call center of mass to make a point. Okay? This point is often called center of mass. And we'll talk more in detail about that when we get to that chapter. But we can represent all things as a point, which makes our lives a lot easier for those of you that are not artists like myself. I don't want to be drawing all these horrible pictures for you. So we can represent them as points, but there's a logical reason why we can do that. Because the molecules squeeze to form that point. Now this is often called particle. Okay, they call this, your textbook calls this the particle model. But I don't put much emphasis on this point. The idea behind the particle model is that, exactly as I mentioned, everything can be represented as a point, which makes analysis of motion a hell of a lot easier. Now, motion can occur as 4 major types of motion that exist. Certainly more, but we'll concentrate on 4 types of motion. The types of motion are linear, circular, or simply curved motion. That doesn't necessarily have to be in a circle. 3 is rotational, something which rotates. And of course, 4th is projectile motion. And we will study each in detail. We'll study each in detail. Now, in this first few chapters, we're going to concentrate on linear motion. We're going to concentrate on linear motion. This is going to be chapter 1, 2. And we'll probably cover a little bit of circular motion, chapters 1 and 2 as well. We'll cover a little bit of it, not too much. And it's also covered again in chapters 7 and 8. Chapter 7 and chapter 8. But we're not getting there yet. Rotational motion is going to definitely be chapters 7, 8, 9. Projectile will be chapters 1, 2, and 3, mostly. Now, just giving you this as a heads up so you know where we're going. First, we study linear motion, then we study projectile motion, linear and circular motion kind of together. Then we study projectile motion, then we study rotational motion last. And we'll talk, everything can fall within those categories, so we'll talk about why that is later. Now, since we have this concept called motion, which is movement, we have to define characteristics that belong to motion. So, the characteristics of motion are as follows. As I mentioned earlier, all motion occurs in time. Another characteristic is that it has a position. It has a position. Okay. And the last thing that it has is, of course, an ending point. Okay. All motion has a beginning and an end. Even in the concept of infinite motion, this idea of beginning and end has to happen. And we'll talk about more in detail why that is in a bit. But for now, you need to know the three major characteristics of motion. It has a position or beginning point, and an ending point, and it occurs in time. For now, this is what you need to know. And we'll add to this list as we get there. Let's go to a new page. We'll define some terminology for us. Definition of position is the location of a body with respect to an axis cardinalette, or angle, etc. Okay? So the idea of a position is that you're going to be somewhere. Okay? Let's give an example. Every physics teacher has a victim child, through which they become the victim of every problem. Mine is my ex-best friend. We'll call her Helen. So, Helen, she's standing. Let's say she's standing at a bar. And walks to her house. Okay. So let me draw a picture. Here's Helen. Okay. Here's our bar. The little dot is Helen. And here's her house. Whatever. Supposed to be smoke, but whatever. Okay, here's her house. So she's walking and walking and walking to her house. So she walks from the bar to her house. Whether she's drunk or not is not the point. Okay? But the idea is that she's walking to her house. She's located at a position, an initial position. We'll say this initial point is often called the origin. And you'll recognize that term from mathematics. Well, mathematics is a tool that we use in physics to help us understand techniques. So the origin is where she's beginning, and she has an endpoint, which is her house right here. Okay. So in this case, I'm on an entirely flat surface. I don't know how to draw, so you'll have to deal with it. Since she's on a flat surface, I can see that she's walking east, right? And you guys are familiar, of course, with the cardinal directions: east, west, north, and south. So she's walking east. So she walks east. So at this point, she's at 0, and her direction is east. Okay. It doesn't. Now, at this point, I'm not defining units or anything, but she's walking east according to according to the diagram that's here. She's walking east to her house, and so she ends up at, of course, the end. We can call it. Let's see, it's like 3 meters to get to our house. So you can call this 3. This is due east. Okay. And we'll give those numbers units later. But the idea is that whenever I'm talking about a position, it's always with respect to something. Okay. On a flat surface, I say north, south, east, west, whatever. It can be at an angle. Let's say, for example, here's a triangle. There's Helen at the bottom of the hill, and she's walking up the hill until she reaches the top, and then she jumps off the cliff. And this is angle theta. In this situation, the bottom is origin, where she begins, and at the top is where she ends, where she ends up falling off the cliff when she follows a projectile path. But that's for a later date. So, in this situation, she's walking, but at an angle. In this situation, I can say that Helen walks at angle theta. Alright, so the circle with the little squiggly line through it, that's the Greek letter theta. We do not recognize that. Okay. So at that point, she's walking with respect to an angle theta. Right? So this is the idea with respect to an angle. And, latitude and longitude from your geography classes, this also involves location and position. This is how your GPS works, right? What is it called? Global Positioning Device. It needs a position. So your location is given with respect to a particular axis or length. It might be 34 degrees north, for example, where we are, 34 degrees north of Los Angeles, roughly. And so it is important that you recognize whenever I'm talking about position, that I'm always talking about the location with respect to something. It's an angle, it's a cardinality, it's something, but it's not, but it's always with respect to something. The idea of change in position is what we call displacement. Is a change into the sun. The change in position simply. So, in my second example, she changes position from the bottom of the hill to the top of the hill. This is a change in position. She's no longer in her original position. If I go back to the previous example, she changes her position from the bar to her house. So there's a change in position. She's no longer at the original place she was located. It is certainly possible to go back to your original position. Okay? It is not required that a change of position take place. But a displacement always represents the change in position, movement from one point to another. It can be the same point, but it's always a movement of some type. Displacement represents that change. Okay? And not to be confused is a word called distance. Which is the total length that's traveled. Okay? So, in the case of Helen traveling from the bar to her house, okay, so she travels from the bar to her house. The distance traveled is going one direction. Here. She doesn't turn back. Now, let's say she went from her house to the Twin Towers jail. Okay. So now she's traveling from her house to jail for some odd reason. Who knows? Now, then she ends up way up here at the top floor. Okay. Now, in this situation, the total length traveled is again one way. But then, let's say she decides to go back to her. Let's say she decides to go back to the bar. So she goes from here, 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 and then here, and so there, back to the bar. Now, since you traveled back to the bar, the total length traveled is the red arrows plus the green arrows. So she was totally in length on the red and totally in length on the green. So the difference between distance, so the distance is the red plus the green. Okay. So I'm going to put a little green line like that. Okay. So the red plus the green is the total distance. The displacement is 0 because her original position does not change. She ended up right back at the same point she started. Do you see the difference? Displacement has to involve a change in position. If there's no change in position, there's no displacement. So that is an important thing to keep through your big little heads. No change in position, no displacement. Write that down. Okay. Okay. Now, mathematically, displacement is represented by the Greek letter capital delta x, which can be written as x final minus x initial, such like this. So this is mathematical definition of displacement here. And you guys are algebra savants, so I don't need to tell you how to do that. But we'll talk about what it is. We'll talk about what it is in a little bit here. Okay? We'll talk about what it is in a little bit because I want to define things consistently here. And the last concept I want to talk about today is time. Now, time is a very strange consideration. We often speak of time as a subjective thing which is created by a man's whims or whatnot. This is not true at all. Time is completely ordered. So, time has an ordered quality to it. Which, sadly, we don't get to study the order of time until we get to quantum physics. For now, you have to accept it as such. Time tells us when something takes place. So, when, in this case, motion, takes place. Time tells us when that motion occurs. Notice I'm not giving you any real mathematical definitions here. Now, time for our purposes is always positive, but we can discuss later when we get to quantum physics how that might not necessarily be true. But for now, we'll work with this. Okay. And a time interval is the change in time that takes place. Okay. It's the change in time that takes place. For example, I want to wake up at 8 o'clock in the morning. And as I'm sure you guys are very familiar with, your clock has a snooze button, which I'm sure you're all very capable of pushing, and more often than not push on a daily basis. That interval is about 10 minutes, right? Depending on your clock, obviously. Now, the time interval between when the alarm is going off and your snooze button is about 10 minutes. So in this case, there's a time interval change. The time to change is about 10 minutes. So we'll talk about the units of time, of course, later. Now, I want you to get this idea through your head. Time intervals are always positive. We do not have a situation, insofar as you know, insofar as we're going to talk about in this class, where the time change is negative. Now, it's not always going to be true. When we get to quantum physics, I'll explain some other properties about time. But time is ordered. It has a direction. Okay? Time must have a beginning. By its very nature, the very characteristic of time itself means it has to have a beginning. And how do we define this beginning? We'll talk more about that tomorrow. So for your homeworks for this class. So we're going to do some questions. And so I want to do some examples really quickly with you before we move on. Of how to do a motion diagram for a problem. Alright, so it asks you how to draw a motion diagram. Okay. So let's draw a motion diagram for a person driving a car for 10 minutes, then fixes flat tire in 2 minutes, and then drives for 3 minutes. Now this is a very simple problem. Alright, so the first thing I want to do is, can I represent it as a point? With a car, absolutely it can be represented as a point. It can be represented as a point by squeezing the molecule like this. So the molecule is squeezed, and so they're driving in the car for 10 minutes. You can draw a length of an arrow like that, and then fixes it flat for 2 minutes. So if there's fixing a flat, there can be no motion, right? So the car stays stationary for 2 minutes. It doesn't have to be perfect. This is a 10-minute interval. And this is a 2-minute interval. And then like this again for this is 3 minutes driving. So does that make sense? Where motion doesn't take place, you just draw a point. And when motion takes place, you draw the arrows. Okay? So that's doing motion diagrams. And so for your homework for today is to read pages 1 through. Read page 1 through 8. Read pages 1 through 9. And then I want you on page 13. And then I want you on page 'I want you to attempt equivalence. Page 26 to attempt the problems numbers 1 through 3. And we'll do more tomorrow. Okay. So good luck. And hopefully all things that I've said in this lecture make enough sense for you to do.